Okay, welcome to January 12th, Wednesday Yaskawa IQ training class. And today we're going to have a little bit of a review of some of the adventures that we've had over the past month in terms of our interface with the customer base. And we're going to focus on power issues. The first thing we're going to tackle today is the issue of Open Delta. And my colleague, Craig Swift, is with us today. We were having a discussion before I started the recording. And Craig's got a lot of experience in the field, especially with PG&E. So before we get into Open Delta, though, Craig, you said that you're meeting with PG&E and that there may be some potential for movement on the PG&E specification for power rebate.
Yeah, I've got an initial contact that I've been working with, and she's out of Northern California, and she's trying to push this rebate, and she's been having issues. And she kind of reached out to multiple people, and I got hooked into it and started talking to her, and they're now realizing why they're having a problem with, pushing this rebate, because one of their recommendations to lower harmonics is to put on a load reactor. And when I explained to her why that was wrong, she was extremely shocked. So,
no way.
Yes, these people are not electrical engineers. They're not even electrically, how do you say, proficient.
All right, well, they're customer interface business people then.
Yeah, pretty much customer service reps. So we're going to meet with them. She's got actually two other people that I've not interfaced with yet. We're all doing this again, preliminary, so we can discuss. Basically, I blindsided them with the matrix technology. They had never seen it before, and they're just astounded.
Okay, but as far as them, I mean, matrix isn't even on their map as far as their spec for the power rebate. And so far, have you seen anything other than the power rebate specification that is addressing the harmonic distortion issue officially from PG&E?
No, it's all been basically innuendos. They are moving this way. In fact, one of the words that triggered them really quick was power factor penalties. When I told them that the matrix was used in other states to combat power factor penalties, they lit up. They did not make, you'll love this, person, they didn't make a correlation between harmonics and power factor.
Well, again, you're talking to non-technical folks.
Yeah.
Hopefully we will be able to address this with the technical people who write the specifications. What was a little bit disturbing to me was that this specification was outsourced as opposed to being written by staff engineers at PG&E who have all the experience. But
right.
that's
so they're willing to. I've gotten a couple customer service reps saying that they're pushing back at PG corporate, saying that, in the previous rebates, they've always found that installing our product versus other products results in less man hours invested by PG&E.
Why is that?
Because we go in and basically they don't get a callback, whereas if another product goes in and they get callbacks, PG&E gets in the middle of, hey, this thing isn't working. They're like, well, it's not us, so we just give you the rebate.
Okay. Well, that's some progress. I can see. I mean, we definitely have to get, in general sense, we have to improve the power factor on the grid to make best use of what we have. The fact that one of the major utilities is moving, albeit perhaps not at the pace we would like, in that direction is positive. And I think that both Yaskawa or Yaskawa and some of our competitors have some pretty good solutions once PG&E motivates the customer base and the cost structure to require those sort of things. I mean, you know, you got to buy a raincoat if you're going to go out in the rain and stay dry. And PG&E needs to tell people they need to have the raincoat. But okay, so that's a thank you for that update. I'll continue to poll you as we go through the year on these classes. Today, you can see my screen, hopefully, and the first subject we're going to deal with is something that came up for me in a couple times in the past couple of weeks, and that is the Open Delta. Oh, hang on a second. There we are. Craig, you made a surprising statement to me earlier this morning when you said that what percentage of three-phase transformers you're seeing in the field are open delta?
60 to 65% of them, because we're just in an area that has open delta.
And that area would be?
Basically anywhere from probably Tulare north.
Wow.
And heavily concentrated in between Salinas and Napa. That's where the majority of the phone calls that I get on open delta systems come from. And we got one guy up there, he installs usually 60 to 100 drives a year, micros, which is where we prevalently run into the problem. He'll install 60 to 100 of them, and we'll usually get 3 or 4 of them out of the group that have a single phase and fallback issue.
I'm surprised at that, frankly. I find that a little bit disturbing because the open delta transformer requires upsizing of the drive. The voltage variances on it are significant, and okay, well, let's deal with this. Open delta transformer. When you identify that you have an open delta transformer, and typically it's going to be a 2-can system off of the power pole. It can be a single can system if the can, you can see that the there's only 3 lines coming off of this and 2 windings. This is an unbalanced 3-phase system, and the imbalances increase as you increase the load. So knowing that we're feeding a 3-phase 6-diode bridge on the input of the drive, you're going to stress some of the diodes and not others. We're going to have unbalanced heating in the diode bridge. There will be more DC bus ripple, similar to the more severe single-phase input case, and therefore we will stress the capacitors. In a situation like this, where there's a drive inserted right here, I hope you can see my cursor, the motor, whether it's a Y winding or delta winding motor, will not see the imbalances. That's a very important point, because the drive isolates the motor from those imbalanced characteristics, because the drive takes the 3-phase power line, creates DC, and then creates through the inverter section a balanced 3-phase AC output to the motor, at least as far as current is concerned, because the motor winding has balanced impedances. Therefore, we have a situation where in submersibles and in above ground pump motors, the motor is relieved of the effect of open delta, but the drive now becomes the sacrificial lamb. And there's an article a nice article that was written by one of our colleagues at Yaskawa. And this is the article. I will include the link in the documentation associated with this class that you can access as a member of our team. And basically, Dan has gone over the details of the effects of the open delta system on VFDs. I'm going to jump to the conclusion and tell you that our recommendation on the sizing of the VFD is to put an input reactor in front of the VFD to add some impedance to the circuit. And a DC bus choke is acceptable if the drive comes with its own DC bus choke installed. That would be the equivalent of a three-phase input line reactor. If you put both on, you get about 5% equivalent input impedance, and that's acceptable. More than that is not. And then we recommend that you size up the drive one frame size. So if I'm looking here at the IQ 1000 catalog, and you can see that here at the 380, 480 volts, so for us 480 volt US voltage model line, we have different output amp ratings, which result in different part numbers, but these heavy lines indicate a frame size change. What that frame size does is when we go from 2.1 to 4.1 amps, the frame doesn't change. Therefore, the capacitors in those two models are the same. We're looking for increased capacitance because an open delta system increases the voltage variance, the voltage ripple on the DC bus. Therefore, we want more capacitance. So we need to go across the line. And taking another example, if I have a 75 horsepower application and an open delta transformer, the recommendation is to go to a 125 horsepower drive, skipping over the 100, because the 75 and the 100 horsepower IQ have the same capacitors. The 125 has the next size up capacitance. So again, for open delta, we recommend impedance, 3% or 5%, and we recommend sizing up one frame size to get the extra capacitance needed to deal with the increased DC bus ripple. Now, that's a halfway measure to what we recommend in the case of a true single phase input. In the case of a true single phase input, the D-rate is much more severe. Again, taking the 75 horsepower application, which you can see in the part number here, is a 103 amp drive that corresponds to the column for rated output amps. So a 4A, 4 being 480 volt, a 0103 is a 103 amp drive. That's the 75 horsepower three-phase application. If we go to the single phase version of that and we go to 75 horsepower, we will see that we are in a 362 amp drive without additional reactor. And if we add an additional reactor, the 75 horsepower application will require a 296 amp drive. That's a significantly greater D-rate, significantly greater cost necessary to deal with the more severe limitations of a single phase source that the drive is going to get, because now we're severely imbalancing the load on the diode bridge. 2 of the 6 diodes aren't even conducting. And the DC bus ripple, as a result, is much greater. Therefore, the capacitors are working much harder. Failure to do this risks the overheating of the capacitors and the overheating of the diodes. In my experience, in single-phase applications, the capacitors are the first ones to go. Craig, correct me if I'm wrong, but the diodes are a little bit hardier. And when the capacitors go, unfortunately, we do not have capacitor thermal sensors. The tops of the capacitors will heat up quickly in a single phase situation where the DC bus ripple is extreme compared to a 3-phase input. And because capacitors are voltage shock absorbers, we're basically running them over a really rough road. We don't have a sensor to sense the temperature on the caps. Therefore, this leads to a catastrophic failure, as opposed to the mantra that we try to hold in our design, which is fault trip before component failure. Because we do not have the sensor, we cannot fault trip. That's why this situation is much more severe, and it is very important to comply with the guidelines that Yaskawa gives you for these various unbalanced power supplies. I will say that if we treat open delta as a single phase and size up severely, then we're safe. If you want a rule of thumb, anything other than a balanced 3-phase power supply, which we want to see as delta primary, Y secondary, with the secondary tap on the center tap on the secondary grounded. And I will put that up right now. Bear with me 1 second. This is what we want to see. We want to see 3 lines coming into the primary on the power pole transformer, and we want to see 4 lines going out. This ground is critical. I'll explain why in a second. And we want to see balanced impedance on the secondary of that transformer. Delta primary, Y secondary, with the center tap of the Y grounded. This is ideal. This is what you should see in new equipment installations. A lot of this other stuff that we see, the open delta included, is legacy stuff. It was done for cost savings reasons. Craig, are you seeing any more new installations coming out with open delta?
No, in fact, PG is trying to force everybody to 460 so we can get rid of the problem. Which of course exacerbates harmonics.
Now, is open delta primarily seen in 230 volt 3-phase applications?
Primarily, yes.
Okay, well, that's a good thing to note. So if we go back up, our discussion has been on open delta, and our recommendation is size up 1 frame size, not 1 size, to get the extra capacitors, and put 3% or 5% input impedance on the application. What we want to see is a 4-wire situation. Again, a couple of power pole pictures, and there's all kinds of variations out there. But one thing I would like to say is that it's really important that you look up at the power pole when you make an installation. It's critical that we understand the power pole configuration for obvious reasons. Here we've got an acceptable 3-can situation with critical 4 conductors coming off this thing. This you can assume is in most cases, going to be a delta primary. There's the three-phase high voltage leads, and then you have your secondary transformers, three windings on the power pole, three phases, and a ground. This, if you count, we have 1, 2, 3. This is an interesting aberration. I've seen this for open delta also, because if you go back and look at the configuration here, 1, 2, 3. So that's another warning. If you don't see 4 lines coming down the pole, you need to call your Yaskawa person, and we need to discuss the application with you to make sure that you're safe. These are single can 3-phase, but again, you can count the 4 lines. Here we have 4 conductors, the 3 phases and neutral. So a single can versus 3 can configuration can still be a balanced, grounded supply coming off the pole. The single phase stuff, which is more severe than open delta, and the first one that obviously a single phase transformer is a dead nut single phase source, but there are 3-phase supplies out there that have to be treated as single phase and therefore more severe than the open delta configuration. And they would be, the first one is what we call, this isn't corner, center, this is stinger leg is the term for it on the left. It's a delta secondary. I'm just showing the secondary of the transformers now. This is called stinger leg because one side is center tapped, the winding center tapped and brought to ground. This is a way of, again, saving a conductor. These are obsolete systems. They're not being installed on new equipment anymore, but they are still reasonably prevalent in the rural areas of California. The second one is corner grounded delta. In other words, another method of picking up the ground. These were prevalent in the times when most of the usage in the agricultural area was single phase and then some 3-phase loading. And honestly, when you put motors on this, they're seeing their imbalance, and the motors basically took it and had reduced life. You put a drive in there, and as I said earlier, the motor is now relieved of the imbalance, but the drive must take it. And in the case of the drive is a little bit less tolerant. It'll either trip out or pretty much blow up quickly, again, because of those capacitor heating issues. So when you run into a stinger leg or a corner grounded delta, you must go to the single phase sizing that I showed you on the sizing of the drive. And in this case, we publish, and this will be on the documentation associated with this class that you can access on your team's membership. But our single phase sizing is based on something other than rule of thumb. A lot of people still believe that you can use a rule of thumb in sizing VFDs. And during my career, which has spanned a relatively long period of time, that rule of thumb has changed. Early on, we used to say size up 1. Then it became double the VFD. Then it became triple the VFD. And then we said, no, we're not doing rule of thumb anymore because we're not addressing the issue with this general rule of thumb practice. The issue is we want more capacitance. And because, as you can see, sizing up 1 doesn't get you more capacitance. So in the case of a 40 going to a 50, you're not helping the situation. And in the case of a true single phase load, going from 40 up to 60 or 75 and getting the next class of capacitance isn't going to be enough in many cases. What happened is UL came out and said, okay, we are going to have a separate rating for VFDs based on the power supply. And when it's three-phase power supply, we can use these ratings. But when it's single phase, again, 75 horse, 103 amp. When it's a single phase application, these are the UL approved ratings for the Yaskawa product. Every manufacturer should have gone through this. And therefore, when you have a single phase application, you must ask for the manufacturer's UL rated single phase model. And in our case, it's a 362 amp drive without a reactor, and with a reactor, it's a 296 amp drive. You can see that up here in 103 amp, which is the normal 75 horse three-phase, we've gone up 2 frames if you have a reactor on the input side, and 3 frames if you do not have a reactor on the input side. So we don't use rule of thumb anymore. We must go based on the manufacturer's UL sizing for single phase sources. Okay, now, excuse me. Again, this is what we're looking for. And when we're looking at this with a nice balanced supply, we don't really need anything else on the input of the drive. From the standpoint of power-based filters. Above a certain horsepower rating in our product, and I believe that's above 40, correct me if I'm wrong, Craig, we already will install the equivalent of a 3% input line reactor. It's called a DC bus choke. And while it's in a different part of the circuit, the inductor is placed on the DC bus positive rail. It is the electrical equivalent of a 3-phase input line reactor. So when you have a balanced Y secondary with center tap ground, you don't need to add anything else from the standpoint of power filtering to protect the drive. The capacitors will be happy, the diodes will be balanced, they will be happy, and we can move on. However, there are other things that we recommend because of other issues in the power supply, even if you have this configuration on your power pole. Now, the first thing that I will recommend is that voltage, the issue of voltage and how it varies in the rural power supplies, unfortunately, you get a lot of variance, and we're talking about spikes and surges. A spike is a short duration, aberrantly high voltage. So if you chart voltage over time, a spike will look like a sharp pyramid, and there will be a certain area under the curve which represents the area under the triangular waveform shape, which represents the power behind that spike. And because the spike goes up sharply but comes down sharply and has a duration of milliseconds, there's not a lot of power behind that spike. So the drive, as a standard, has a metal oxide varistor between each phase of its input. And if you look carefully on the input of the drive, preferably not when the drive is powered up, you will see these green or blue or red lollipops, and you will see that each leg of the 3 lollipops are between a phase. These are not in line as far as the power is concerned, they're phase to phase. So they're there to clip voltage. And the way that a metal oxide varistor works, varistor is a shortened form of variable resistor. And as the voltage goes up, the varistor increases its resistance. And at a certain point called the clipping voltage, it effectively shunts the higher voltages phase to phase across its resistance, which has increased as the voltage has gone up. Varistors react relatively quickly, and they are suitable for fast spikes. Because they're only the size of a lollipop, they don't have a lot of mass, and therefore the energy they can absorb is limited. A varistor on a 460 volt drive is going to start effectively clipping somewhere around 1,000 or 1,200 volts, and if there's not a lot of area under the curve, it will suppress that voltage from going through the diodes and getting onto the DC bus, and it won't blow up. If that voltage waveform has a greater area under the curve, which would occur with multiple spikes, therefore adding the area of the curve under the curve of all the spikes, or what is no longer a spike but now a surge, the metal oxide varistor will receive too much energy across its resistance and it will fail. It will fail catastrophically and hopefully will blow open, at which point it won't damage anything in the drive. But if there is a short circuit failure, and that's unpredictable, it's kind of a roll of the dice, you could have some issues, obviously. Normally they'll fail open because the little spindly legs on the metal oxide varistor will melt, as would, say, a fuse. If we have a lot of voltage spiking going on or voltage surges, and why we would have that I'll address in a second, then we need to go to more mass. And our recommendation is to use something equivalent to the product made by Raycap called a strike zorb. And if you Google strike zorb, you're going to see basically 3 half beer can sized suppressors. These are metal oxide varistors on steroids, much more mass, much more ability to absorb the area under the curve of the voltage spike / surge, and as a result, far more effective in protecting the drive. I do not see a situation in the agricultural zones of California where I would not install a strike zorb. I want to be very clear about that. The amount of money to install the strike zorb, typically $700 to $1,000 added cost to the installation, is insignificant compared to the cost of blowing up the drive. Why do we have these voltage variances, and why do we need this extra $700 to $1,000 expenditure? Lightning striking beyond a certain distance from your VFD need not blow it up, but it will cause significant voltage surges on the power line. If you have a strike zorb, you will be able to survive those. It's very hard to survive a direct lightning strike. And there's really not much that we would put in place for that. But lightning strikes in the area, which are very common in the Central Valley, are going to cause voltage surges that will cause damage if you don't have the strike zorb. So that's one reason. The second reason is that when the power grid is loaded up at certain times of the day, especially when they're at the end of the line, which in many cases you are in a rural situation, the power company is going to start boosting the voltage. Or they're going to start switching in power factor correction capacitors. Power factor correction capacitors are a bank of caps that are switched in via contactors. It's an abrupt event. It causes voltage spikes and surges. Therefore, that's the second reason why we would want to have strike zorbs and why we would suggest that you pull $1,000 out of your pocket and throw it into the wind. So I hope that is conclusive on that point. the voltage variance issues associated with this. Desirable three-phase power supply are not as bad as if you're on open delta or the single-phase power supplies or the pseudo three-phase stinger leg corner grounded deltas. When you're on those power supplies, there's even more reason to put strike sorbs in there. Now, the second additional filter that is not necessarily power line is an EMC filter. And an EMC filter is basically a tuned resistive capacitive circuit, kind of similar to its effect in that it is a voltage clipper, but it is tuned for much higher frequency absorption. And the EMC filters, if you were buying the European brands, typically will come standard. And as such, because the European community has much stricter rules with regards to emitted high frequency noise, these manufacturers just include them as part of their manufacturing process. In the United States, we don't have those same rules. Yaskawa manufactures in the United States, and so we manufacture to US rules, and the EMC filter is an option. In agricultural applications, I do not recommend this as an expenditure because most of the time you're far enough out that the emitted noise from the drive is not going to really mess up anybody's AM radios or computers or laptops or whatnot. Therefore, the EMC filter is an option. It typically is a few $100s on a 150 horse application, and I don't deem it as necessary. One thing to be aware of is that on the drives that have EMC filters, some of the designs, the EMC filter is not just componentry and connections phase to phase. There is an RC, resistive capacitive portion of the circuit that goes to ground. If that type of filter is used, and I've seen those type of filters, for example, on the ABB product, I'm not sure if that is the design that Danfoss uses, but it's worth checking. You must ensure that you have a ground on your three-phase supply. If you do not, that little RC circuit to ground becomes your ground. So if you're getting a delta Y, but the center tap is not grounded, therefore you've got a 3-line power pole secondary, you will blow this EMC filter up pretty quickly. It's a caution that I suggest that you ensure that you have taken account of, because the failure will be quick and it'll be expensive. In the case of the delta, if this is a delta primary and then there's a delta secondary, I've seen those type of situations as well. That's an ungrounded delta, and again, if you don't see 4 lines coming off the power pole, that is a potential configuration. And again, you need to take into account the corrective action is really quite simple. You need to find that connection, and they have a note in the back of the ABB manual that will tell you how to disconnect that ground connection on their EMC filter. And then you're okay. So at this point, we've addressed open delta, we've addressed single phase, we've addressed some other input filters. I'm going to teach a completely separate class again on the harmonic distortion filters that are available, but I'm going to address that briefly here, just sort of as a preview, because again, we're talking about what are the things we should be considering on the input of our VFDs, depending on the power supply that we are facing out in the field. I hope at this point I've convinced you that when you install an agricultural VFD, it is now absolutely necessary to determine the nature of the power supply. You just cannot go out with a feeling of impunity, because the consequences are hardware failure and additional significant costs. Now, again, since the subject today is about input filters that we would want to consider on a standard VFD application, when the subject of harmonic distortion compliance comes up, and as Craig noted earlier, it will be coming up more and more in California, which is why I address this relatively frequently in this class. I think I will, on the schedule that I have, I've probably got a session for harmonic distortion every quarter in detail, and I mention it as frequently as Craig advises me that there's been a change in the situation with the power utilities. So it means more hardware on the front end of the drive. In the last few minutes of this particular class, I'll speak generally about the situation. The fact is that that six pulse diode bridge on the front end of the drive causes a lot of distortion going back to the line. That's harmonic distortion. The power company wants us to pull current in a perfectly sinusoidal fashion. And when we put an oscilloscope on the current waveform, we see a sine wave. A diode bridge does not create a sine wave. In the class that I hold on the diode on harmonics, I will have detailed pictures of the oscilloscope readings that you can see. But it basically, instead of looking like a sine wave, it looks like a two-humped camel. And that produces a lot of harmonic distortion back to the power grid that causes a lot of bad things, including reduced efficiency on the power grid and heating up of other components. All these things on the power grid that is right now, frankly, more stressed than anybody cares to admit. The best way to increase capacity and increase efficiency on the existing power grid is to address the harmonic distortion issue. That's why we're dealing with it. So what we want to do when we install a VFD onto the power grid is we want to minimize the distortion of the current waveform. The other form of harmonic distortion is distortion of the voltage waveform, and a 6-diode bridge VFD does not create a lot of voltage waveform distortion, so we can pretty much put that aside. One other thing I should mention is that total power factor consists of two methods of messing up the waveform, if you will. One is displacement power factor, the other one is distortion power factor. I've talked about distortion power factor in the last few minutes, both on the current and voltage waveform. The other type of power factor distortion is displacement power factor, where the waveform for the current, when it's charted on an oscilloscope over time, is not in phase with the voltage waveform. And in most cases, as you load up the power pole transformer with an inductive load, the current waveform is going to lag. That type of distortion is also not a concern of a diode front-end drive. So, of the three basic types of distortion that we want to be associating our discussion with, displacement power factor, not a problem with a diode front-end drive. Voltage distortion power factor, not a problem. Current waveform distortion power factor, the third item in total harmonic distortion and total power factor, current waveform distortion power factor is the concern. And the way that we are going to fix that, first thing we pull out of the holster is inductive reactance, copper wound around iron. because a capacitor is a voltage shock absorber, an inductor is a current shock absorber. And therefore, when you have aberrant current waveform, you pull out a shock absorber. And the first thing that you do is you throw an input line reactor onto the front end of the drive. Now let's put some numbers on this. The distortion of, and in the session on harmonics, you'll understand a lot more about what these numbers mean. For the sake of the conversation today, let's just value them in relative terms. The ideal distortion is 0. The distortion of a drive mounted onto the power grid, measured at the terminals of the drive, with no filters, is 70%, give or take. That's pretty significant. Certainly not acceptable. By the way, the acceptable levels are defined by IEEE 519-2014, and typically they are 5%. So a naked drive on the power grid is 70%. If we put a DC bus choke or a 3% line reactor on the drive, we can drop that to 30 to 40% at the drive terminals. If we add a tuned harmonic filter, which is basically a reactor with some tuned RC circuits phase to phase, basically a low frequency EMI RFI filter, we can get that down into the 20% range. Some of the manufacturers are saying they can get that down to compliance with IEEE 519. I am only going to say that I'm a little skeptical of that and like to see that proven. Remember, we're dealing with passive filters here. The input line is a dynamic thing. And as such, a passive filter is going to work best in some circumstances and not best in others, as the line dynamics move away from the tuned point of the passive filter. If you're a catcher and you can't move your mitt, you're only going to catch a certain number of baseballs coming at you from the pitcher. This is the case here. We will talk about active filters in the harmonic distortion class, because there is technology that reacts quickly enough such that the catcher can move the mitt and catch all the baseballs. It's not part of the scope of today's class. So passive filters, we have talked about no filters. We've talked about DC bus choke. We've talked about 3 and 5% input line reactors. We've talked about tuned traps. And the next step up from that, which gets you down into the 12% distortion range, is the 12 pulse filter. And this requires 2 rectifiers, 2 6-diode rectifiers on the drive. So if you have a 6-diode drive, you got to add another rectifier. And the outputs are connected to the positive here and negative rail of the DC bus. Excuse me. The transformer itself is different from the power pole transformer. This is an additional device that you add in. And it's going to be big because the power runs through it. So it's going to be sized for the power, and therefore vary in size the same way the drive varies in size and the same way the motor varies in size. From a mass standpoint, you're going to have about the equivalent amount of copper and iron as the motor itself. So it kind of gives you an idea of the size of the device you're dealing with. You have a 3-phase line input into what amounts to 2 3-phase outputs, one into one rectifier, one into another, and the resultant DC bus to the capacitors of the drive. What they in essence do is they shift the 3-phase output between the 2 secondary windings anywhere from 5 to 15%, 5 to 15 degrees. So when you're looking at the output waveforms from this 12 pulse transformer, you cannot connect X1 and X2, even though they're in essence the same phase, because these transformers have shifted them such that the voltages are not in sync. And therefore there will be a voltage potential at all points except 2 on the relative sine waves. So you dare not connect these three-phase supplies together, but once you rectify them through the 2 separate rectifiers, everything is DC and it can be connected on the output. Now, this particular diagram is not accurate for the type of 12 pulse that we use at Yaskawa, because it shows rectifiers in series and we use rectifiers in parallel, but that's a small detail that we'll pick up during the harmonics class. Bottom line is, for the sake and scope of this discussion, a 12 pulse dual rectifier front end configuration gets you reliably into the 12% range of distortion. If you want to comply at the drive terminals using passive filters, you would need 18 pulse, which means there's a third winding and another rectifier bridge. And Yaskawa carries 18 pulse systems in their catalog, as do most of the other major manufacturers. This is old technology. This is passive filters. It is not compliant at all times. It is not compliant at all load levels. There is active technology out there, active front end drives, AFEs. Cost-wise, they're probably 20% more than the cost of an 18 pulse system, but you get compliance to IEEE 519 under all the critical situations, regardless of the variation of the power line, within reason. So that's where I'm going to leave this discussion today. And hopefully we've had a decent review of some of these issues. The main point of this class is to get you to look at the power pole when you do an installation, or if you're in the design mode, to make sure that you know what the power pole configuration is. I realize that there's design modes for new construction, in which case you can reasonably assume, although assuming is always dangerous, that the configuration will be the desirable delta Y with the center tap grounded. Verifying that is important. If you are going into existing installations, especially in rural areas, please check and make sure. Because as you've seen today, the equipment and the cost associated with that equipment, let alone the consequences of not having correct configurations, can be significant. I hope I've been helpful today, and it's now 8:03 and it's time to go to work. Thank you for attending, and I'll put this class up for recording on the Teams landing page. Thank you very much.